Before deriving the maximum power theorem, I'll give a quick overview of the problem and the primary result. The general idea is that we want to transfer the maximum amount of power from some circuit to a load. I'll use a resistance, RL, as my load. Thevenin's theorem allows us to generate a general result from a simple specific circuit. Thevenin's theorem tells us that any linear circuit can be represented by a voltage source in series with a resistor. So this circuit can be used as a model for any linear circuit. We want to find the value of RL that transfers the maximum amount of power to the load. In order to do this, we choose the load resistance RL to be the same as the Thevenin resistance RTH. This is an important problem because there are two potential ways for this circuit to dissipate power. Power can be dissipated inside this circuit as heat created by the Thevenin resistance, or power can be dissipated outside the circuit via the load resistance, RL. If we think of this circuit as something that we're using to deliver power to our load, we don't necessarily want to use up the power inside this circuit. For example, if we connect a set of loudspeakers to an amplifier, we want to use the maximum power possible to produce sound, rather than wasting power to create heat inside the amplifier. So when you buy speakers to connect to an amplifier, you choose speakers that have a resistance that matches the amplifier output resistance. If your amplifier impedance is 8 ohms, you connect 8 ohm speakers to it. Otherwise, you're using the power amplifier to heat the room rather than to produce sound. Now I'll do a quick derivation of the maximum power theorem. We'll base the power dissipated by the load resistance on the load voltage VL. The load voltage can be determined via a voltage divider formula. So VL is equal to VOC times the load resistance RL over the sum of the two resistances RL plus RTH. The power dissipated by a resistor can be calculated as the square of the resistor voltage divided by the resistance. If I plug this equation here in for the load voltage, I get this equation. To visualize this equation, if I plot power as a function of resistance, I get this red curve. The maximum power transferred is here, and we want to find the value of the load resistance that dissipates this power. To maximize a function, we set the derivative of the function equal to 0. Since the power is a function of multiple variables and we want to maximize it relative to R sub L, we take a partial derivative with respect to R sub L. Substituting the previous expression for power results in this. We can use the chain rule to perform this derivative, which results in this expression. To minimize this, we can set the numerator equal to 0. There are two possibilities that result in this. The first is to set RL plus RTH equal to 0. This solution has a couple of problems though. The first is that it requires a negative load resistance, which isn't physically possible. The second drawback is that it results in a 0 denominator, and 0 over 0 is undefined. The other possibility is to cancel out the RL plus RTH term in both the numerator and denominator. So this goes away, that squared is eliminated, and this becomes a cubed. Now, this is RL plus RTH minus 2RL over RL plus RTH cubed. Setting the numerator equal to 0 now says that RL plus RTH minus 2RL is equal to 0. And solving that for RL results in RL is equal to RTH, or that the load resistance should be set equal to the Thevenin resistance of the source circuit. Now that we know what the load resistance should be in order to absorb the maximum Now that we know what the load resistance should be to absorb the maximum power, let's determine the amount of power that's absorbed by the load under that condition. The load power is determined from the original expression we had for power. If we choose the load resistance to be the same as the Thevenin resistance, RL over RL plus RTH becomes 1/2. 1/2 squared is 1/4, so the power delivered is VOC squared over 4 times the Thevenin resistance. Now let's do an example. We have a load resistance that we're connecting to this circuit. We want to choose a value for this resistance that absorbs the maximum amount of power from this circuit. After that, under that circumstance, we're going to find the maximum power that's delivered to this load resistance. So the load resistance is going to be the same as the Thevenin resistance seen across these terminals. So my equivalent resistance is the resistance of this circuit with these sources killed. The current source becomes an open circuit, the voltage source becomes a short circuit, and these two elements are in parallel. So Req is equal to 2 ohms times 1 ohm, the product of the two resistances, over the sum of the two, 2 ohms plus 1 ohm, which is 2/3 of an ohm, which is the Thevenin resistance seen across those terminals. So to get maximum power to our load, we'll make the load resistance 2/3 of an ohm. Now let's calculate the power that's dissipated by that resistance. Our equation for calculating the load power was PL is equal to the square of the open circuit voltage divided by 4 times RL. To get maximum power, I set RL equal to RTH. So I need the open circuit voltage across these terminals. If I open circuit the terminals that the load resistor is connected to, there's no current there. If this current is 0, these two are in series, I know the voltage across a series combination, and I want the voltage across one of the resistors. That's a perfect application of a voltage divider. For this particular case, the 1 amp source doesn't matter because this voltage source is setting that voltage difference. So VOC, according to a voltage divider, is the total voltage, 3 volts, times this resistance, 1 ohm, over 1 ohm plus 2 ohms. 3 over 3 is 1 volt. So the load power, PL, is VOC squared, so 1 volt squared over 4 times RL for maximum power. RL is RTH, which is 2/3 of an ohm. 1 over 8/3 is 3 over 8 watts. Thevenin's and Norton's theorems have a lot of applications since they allow us to derive general results using a simple specific circuit, as we did with the maximum power derivation. We'll use this capability repeatedly throughout the rest of this course.